So, welcome back again to the course on architectural design of ICs. So, we are discussing about the techniques for increasing the operating frequency of any circuit when we have done or we have completed or after completion of the all the architectural optimization or algorithmic optimization. Then there is another way to increase the operating frequency or the sampling frequency of that particular circuit. So, for that we have employed this technique which is named as pipeline, and again I need more improve or that means increase in the operating speed, I have to employ the another technique which is parallel processing. Okay. So, we have learned the basic ideas of that, what is the meaning of this pipelining technique and the parallel processing. Here today again we will take one of the example and we will see how basically this helps to reducing in real time, how it is basically helping me to increase the corresponding speed of the system or that means the sampling frequency or the operating speed of the system. Okay. So, now let us consider we will take one example, okay, and consider one particular block where I am having, let us consider initially I am having one, suppose this is one block which is basically taking 12 nanoseconds of delay. Okay. So, this is the critical path of this particular block. So, this is black box. So, I do not know the functionality as of now. Now, how to, that means after all this architectural optimization I have done inside this black box. Okay. So, now how can I again improve the, that means how can I reduce this particular 12 nanosecond so that I can achieve the, that means that performance on the higher side. Okay. So, this after that means analyzing or after observing this black box, what I found that there is, let us consider 3 combinational blocks, they are connected. So, this is combinational block 1, this is combinational block 2, this is combinational block 3, and let us consider this takes 3 nanoseconds of time, this takes 5 nanoseconds of time, and this takes 4 nanoseconds of time for the computation, and as these are connected to each other. So, that is why it is taking from the input, this is the input and this is the output. So, from the input to the output, the time, total time is taken as, total time is taken as 3 plus 5 plus 4, that is equals to 12 nanosecond, which is the delay for this particular blocks. Now, what I said, in the pipelining technique we will try to put the resistor in between these blocks. Okay. So, to make this particular, here what is happening, there is a data dependency because the C2 is processing the data from C1, the C3 is basically processing the data from the C2. Now, I will, if I put the resistor in this path and this path, at that time this will work as individual, this will work as individual, this will work as individual. How this will work as individual? There is a data dependency, but at that time the resistor will hold the value for one particular clock. So, that means once this is done, then this will be stored at this particular level, that means resistor. The previous value of this C1, that will be now processed in C2, and then again this resistor will hold the value, corresponding value, and C3 will consider the previous holded value of C2. So, that means the if I have not put this resistor, so at that time what was happening, whenever C2 is giving that means output or producing the output, immediately there is a change in the C2. Whenever C2 is producing the data, C3 is immediately processed. So, that is why the total, that means time is basically added to 12 nanoseconds. But as I have put register, there it is not that though C1 has processed the output or how much time it is taking to process that C1, that means for this C1 process, it is not at all dependent or it is not affecting the corresponding C2. It is basically affecting what? The previously holded value for C1, which is stored in this particular register. So, that value is now basically coming to C2 and that is changing the value of C2. Okay. So, that is why the data dependency is basically broken by putting this extra register in between these particular blocks. So, at that time now for, if I just suppose, then I am having the blocks something like this. Let me draw the block first, then again we will discuss. This will be connected to this particular register and this is nothing but the clock, this is the input and this is the output. Okay. So, this is C1, this is C2, this is C3. So, this is taking 3 nanosecond, this is taking 5 nanosecond and this is taking 4 nanosecond. Okay. So, I have put 2 registers in between. Now, what will be the corresponding critical path of this system now? That is, what will be the minimum clock period which I can consider for this particular case? What will be the clock period? What clock period I will set over here? So, the minimum clock period which I set, that is this max of the delay of TC1, TC2 and TC3. So, that is max of 3, 5 and 4, which is 5 nanosecond. So, that means initial requirement was 12 nanosecond, but after putting this registers in between this path, now I have come down to, that means after doing the pipelining, now my clock period, this TC becomes 5 nanosecond. So, initial circuit was something like this. At this particular point I am having this register. So, here I was having a register. So, this is the input and this is the output, okay, and this is the clock. So, this is requiring 12 nanosecond. So, that means the clock period requirement for this particular case, that was 12 nanosecond, but now it becomes to 5 nanosecond. So, then I can say that the speed up is basically 12 by 5, that is 2.4 over here after doing the pipelining. Okay. Now, I want to increase the sampling speed, or I just come down, that means my requirement of the sampling speed is 1 nanosecond. So, at that time what I will do? Then what I can do, that means at that time if I consider this is as C1, this is as C2 and this is as C3, and there I am having these registers. Let me draw first. So, this is my C1, this is my C2 and this is my C3. Okay. So, there I have drawn it in, that means horizontal, here I have drawn it in vertical. So, that means the input x0, then x1, x2, it is basically coming in this manner to the corresponding pipelining things. and I am getting the y0, y1, y2 dot 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 dot, okay, in this particular case. But what I said, my requirement is, so here the corresponding delay requirement is 5 nanosecond, correct. If I need the clock period to come down to 1 nanosecond, so at that time what I have to do? I have to imply this parallel processing levels of 5. That means, now if I process this, if this is known as one of the processing element, so this will be copied 5 times, okay. This will be copied to 5 times, okay. And then what will happen, this x0 will come over here, x1 will come over here, x2 will come over here, x3 will come over here, and x5 will come over here, and it will produce y1, y2, y3, y4, okay. So, at that time, that means this, if that means if I need to process, or if I have to channelize these particular samples to the corresponding processing element, this is P1, this is P0, sorry, this is 0, this is P1, this is P2, this is P3, and this is PE4, and I need to channelize this proper, that means input to the corresponding processing element, and again I need to combine this particular output to the single output. So, that means here at this particular things what will happen. So, if I just draw this particular circuit, so at that time how it will look like, okay. So, it will be something like this. So, then again I need here this resistor, then again I need to draw C2, then again this resistors I need, and then again I need C3, and here I need the resistors, okay. So, this will be coming to this, 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 this will be coming, and this is the output, okay. So, this is the input is basically coming to this particular point. Now, what I have to do? I have to copy this for 5 times, right, these particular blocks, as I have employed the parallel processing level of 5, okay. So, this is C1, this is C2, this is C3, correct. Now, for this again I need to put the extra resistor over here, and from here I will get y0, from here I will get y1, here this will be giving x0, this will be giving x1, then again for this again I need to draw the corresponding circuit, which are nothing but this. That means I am just copying this particular circuit with the one processing element for multiple times, correct. So, then again coming to this, so this is for y2 and this is for x2, then again for the fourth number of processing element again I need to do the same thing. So, what I have to do? I have to connect this. So, this is for x3 and this is for y3, and at the very end, that means this is the fifth element or the fifth processing element. Here what I have to do is that so this is for x4, this is for y4, okay. And all are, this is C1, this is C2, this is C3, sorry, this is C2, again C1, C2, C3, C1, C2, C3, C1, C2, C3. And what I said, actually my data, they are coming like this, x0, they are coming like this, x0, x1, x2, x3, x4, and I need the output will come like this, y0, then y1, y2, y3, y4, something like this. That means, in the serial manner, the input, the flows of the output and input are in a serial fashion, okay. So, whenever I will put the serial input to the corresponding parallel processing block, so I need one serial to parallel converter at the input of this. So, what circuit is serial to parallel converter? So, serial to parallel converter is nothing but the demultiplexer, where it that means takes the input, one input, and it produce several outputs. And in the same, that means one input it takes and it produce several outputs. So, that is why I need, so serial input is this one. So, now this will come, okay, and it will produce x0 over here, x1 over here, x2 over here, x3 over here, and x4 over here, okay. So, that means now I need the demultiplexer block from where all this will be connected, and the input is basically, which is the, that means input which is coming, this is the demultiplexer, this is the demultiplexer block at the input side which I require. And in the same, that means in the opposite manner, what I require, here I am producing the y0, y1, y2, y3, y4 parallel, but I need the output in a serial manner. So, that means in this case, what circuit is basically parallel to serial converter I require. So, multiplexer is basically does the same, it takes several input and it produce one particular output, okay. So, that means now it will take more, that means at this particular case it will require one mux at the output, where each of these output will be connected to these blocks and it will produce one which is y or yn, okay. So, that means now it will be 5:1 multiplexer, okay, and the silic lines are something like this, okay. So, this is the corresponding circuit for. So, now the clock period of this, that means that this particular sampling speed of this, the input sample speed or this output sample speed of, that means whenever I need to produce this. So, at that time it will be of 1 nanosecond. That means, here actually after that this I require one resistor which will produce the yn. So, this the resistor, okay, not if I do not consider this, then the resistor for this input and the resistors which I require for the output case, both are requiring 1 nanosecond of sampling speed. The internal of this, that will be different, okay. And this clock will be the, they will be connected, and this block is basically, they are all connected to the same clock, and this clock will be the 5 nanosecond, which is the requirement of processing elements critical path, the requirement for this clocks of this register. So, that will be of 5 nanosecond. So, if I that means say that means the clock period of this is 5, these are 5 nanosecond to each of this particular register. So, at that time you see within 3 nanosecond I have completed the job over here, but rest of the 2 nanosecond it is just remain, this block is basically remain idle, sitting idle, where I require at this particular C2 block basically I need 5 nanosecond for computation of this C2 block in each of this case. And again if I that means come down to C3 block, it computes for 4 nanosecond, but it has to wait or it is just sitting idle for another extra 1 nanosecond blocks. Okay. So, that means there are redundant computations or the blocks which are basically sitting idle. So, that means the working that means percentage of this C1 is 60%, okay. This is 100%, that means at all time at that means the clock frequency is 5. So, that means these blocks are running at 100% rate, but this is the working at 8% rate. Why? Because these blocks are basically sitting idle for 1 nanosecond delay, where the clock period requirement is 5 nanosecond delay. This basically is that means sitting idle for 2 nanosecond delay, as the clock period is 5 nanosecond. So, that means the working the corresponding this efficiency of this C1 block, that is 60%, the efficiency for C2 that is 100%, and the efficiency for this working efficiency that is C3 that is 80%. So, from this observing this particular point, so can I reduce this particular circuit? That means can I, that means whenever I am employing these particular elements, that means it consumes the area. If it is sitting idle, I am that means what I have employed, as all the blocks are not utilized or the utilizing efficiency that are not 100% in each of the stages or each of these blocks, that is C1, C2, C3. That means I have put redundant block to the circuit. So, redundant, I have increased the circuit, that means the in operating frequency, by putting what? Redundant circuit to the system. But whenever I have put the redundant circuit, as that is not the utilization, that means efficiency is not 100%. So, that means I am basically losing unnecessarily, I have put those blocks, which is basically costing me more area and more power too. So, can I reduce that? So, that means if I want to reduce that, so at that time what will happen? I need to, that means so that this particular register will run at 3 nanosecond, this particular that means this register will run at 5 nanosecond, and this particular register will run at 4 nanosecond. Okay. So, that means at that time I need the skewed clock which will be connected to this, and at that time if I actually I am just coming down to this that particular circuit. So, at that time what is happening? Basically if I just consider redraw the corresponding circuit. So, at the time after that I have one demultiplexer. So, this is the input, sorry, this is the input. Okay. Then I need 3 of the corresponding C1, C1, C1 block. Then this will be distributed to okay. So, not this one, this will not be directly connected. Sorry, So, this will be again that means connected with one of the blocks which are basically again it needs one demultiplexer where it is taking this and it is producing the corresponding this particular path, okay. And this is C2, this is C2, all are C2. Then again this will be connected to one block which is basically connected to the corresponding, this is C3, 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 and this will be, if I just connect to this, this will be connected to this will be connected to this, okay. Then again this I need to one multiplexer. So, this will produce one single output which is nothing but your Y, okay. So, that means what? That means what? Actually, I have not put those registers over here, okay. So, in between, sorry, in this particular case the register will be placed over here. So, there also these registers will be placed. So, at the input side of these blocks the registers will be here, that means placed. So, that means x0, x1, x2, x3 they are coming something like this. Then what will be the, that means corresponding processing table for this? If I consider the processing table for whole of this system. So, at that time for C1, okay, for suppose this is the PC1, then it will be connected with x0, then x1 for PC2 that will be connected with x1, PC, sorry, this is P1 C1, this is P2 C2, this is P3 C1, it will be connected with x2. Then in the next cycle again it will repeat, okay, it will repeat and x3 will come over here, x4 will come over here, x5 will come over here, then again x6 will be connected over here, x7 will be connected, x8 will be connected over here, and it will run in this fashion. That means with this, from this particular demultiplexer block, so all this x0, x3, x6 that will be coming to this particular processing blocks. At this particular point this x1, x4, x7 that will be connected, and for this P3 C1 this x2, x5, x8 that samples will come for at this particular processing blocks, okay. Then again that will be this 3 input. Now again it will be connected to one demultiplexer, okay, which will be again connected to the 5 of the C2 block, okay. So, 5 of the C2 block means then the corresponding, if I consider P1 C2, okay. So, P1 C2 that it will consider, if this is known as, sorry, that means the corresponding output from that, then again that will be connected. So, how that will be? So, it will be x dash 0 in P2 C2, it will be x1 dash, x1 dash is the output from this demultiplexer, correct. So, then P2 P3 C2 that will be connected to x2 dash, then P4 C2 that will be x3 dash, and then P1 5 C2 that will be connect to x3 x4 dash. Then again x5 will come over here x6 will come over here, x7 at this particular point, x8, x9 something like this will run. This is for this particular case. Again that will produce 5, then that will be connected via this after passes through the demultiplexer, again that will be connected with all these 4 C3 block. Okay. So, then for C3 block that will be the corresponding for P1 C3, it will be as x double dash 0, for P2 C3 that will be x1 double dash, for P3 C3 it will be x2 double dash, for P4 C3 it will be connected as S3 double dash. Double dash is the output from this demultiplexer. Okay. So, then x4 will come over here, x5 will come over here, x6 will come over here and x7 will come over here. And in this manner, for this C2, this x0, then x5, then x9, this will be connected and to this particular blocks. That means, those samples will from this demultiplexer that will be produced and this will come connected to this C2. Then this will be connected x1, x6, then x10 something like this. Then again this will be connected as x2, sorry x11 here. So, x2, x7, then x12. For here this is x3, x8, then again with 5 that means x13. So, x4, x9, then 14, x15, x14. So, again for this x0, x5, x10, x15. So, all this will be come, all these samples will come for this. So, that means now if I just go back to this. So, here what I require is that I require 5 C1, 5 C2, 5 C3, but here in this particular case what I require, I need 3 C1, 5 C2 and 4 C3, and here you see all the blocks are now their utilization efficiency is 100%, that means all the time they are working. So, at that time I have saved 2 C1 block plus 1 C3 block. Okay. So, that means I can reduce the area by this number, reduce the area, and I can also reduce the power too. Okay. So, initially we have started with what? The requirement, the clock period requirement for the initial was black box was 12 nanosecond. Now, I have achieved that is equals to 1 nanosecond of clock period. Okay. And along with that, this the blocks of 3 C1, 5 C2 and 4 C3. Along with the registers are also I have just put extra registers also we have put, that means 3 register for this 3, 5 register for this 5 and 4 register for this. That means, here I have saved 2 C1, 1 C3 plus total 3 register 2. Okay. So, I have that means from this particular point what I can conclude is that I can using pipeline and I can, that means using parallel processing, I can improve the operating speed, and if actually these blocks, the sub blocks, all the delays of those sub blocks they are identical, at that time I do not have to follow this particular architecture, I do not have to optimize. So, whatever circuit, this circuit we have seen, if each of this block is taking 5 nanosecond, there is no chance for further optimization. If these blocks are different, that means the delay for this C1, C2, C3 they are different, at that time there is a chance for optimization. And how we have done that? We have done in this particular case, considering this fact, that means what is the utilization efficiency of that we have find out, and based on that we have just calculated those things. Okay. So, that means by doing these two things together, I can achieve the that means operating frequency I can at the on the higher side, as well as I can reduce the power too by putting the minimum number of redundant circuit to the system. Okay. So, this is one of the techniques or tricks we use to increase the operating frequency of any circuit. Where we have stuck, that means after all the optimization, where we have stuck, still from that particular point I can increase or I can improve the frequency of that particular circuit. Okay. So, for today, this is for today's class, this is it. Okay. So, in the next class again we will see, actually we will start one new topic, which is that means there are several multiplier architecture. So, we will start with multiplexer architecture on the from the next class onwards. So, thank you for today.